Right, in this video, we're going to talk about why some Born Haber cycles are different to sodium chlorides. So you should have already watched the video on sodium chloride, Born Haber cycle. So we're going to look at why they're sometimes a bit different. So first of all, we're going to look at barium chloride. So the first thing we need to do when we do a Born Haber is, if you're not given it in the question, you need to work out what the formula is. And hopefully we can remember from our GCSE that to work out the formula, we need to know the charge on the ions first. So barium's in group 2, so it's barium 2+. Chlorine's in group 7, so it's -1. So that gives us a formula we need. We've got 2+ for the barium, so we need 2 Cl- to give us 2- as well. So that gives us BaCl2 as our formula. So the barium, we've already said, is barium 2+. So that means, unlike sodium, which only goes to Na+, so you only need a first ionization energy, for barium, we need a first and second ionization energy. And for the chlorine, although it's only -1, so we only need 1 electron affinity, so we only need the first electron affinity, because there's 2 chloride ions in that compound, we need to times the enthalpy of atomization of chlorine by 2, and we also need to times the electron affinity of chlorine by 2. So that's slightly more complicated than the sodium chloride Born Haber cycle. Now, if we have something with a 2-, then it looks even more complicated. So sodium's in group 1, so it's +1. Oxygen's in group 6, so it's going to be 2-. So the sodium, because there's 2 of them, you're going to have twice the enthalpy of atomization, I should say, of sodium, and 2 times the first ionization energy, again, of sodium. And then for the oxygen, turning into the oxide ion, we need the first and the second electron affinity. So you need to turn it into O- first, which is the first electron affinity, and then O2-, which is the second electron affinity. Now, from our previous lesson, we should recall that the first electron affinity is exothermic, so it's going to go down on our cycle, but the second electron affinity is going to be endothermic. So if we look at what that affects our cycle, we've got this at the top here. So this is exactly what we would have had before, the gaseous metal ion and any electrons that have been generated by turning it into a positive ion, and then the gaseous non-metal atom. So what we're trying to get to, remember, is this, at the start of the lattice enthalpy of formation, we want the gaseous ion, so 2 sodium+ of the gas and then O2- of the gas. So first of all, we take this O as first electron affinity, and we said that was exothermic, so that's going down. That generates, sorry, I missed the gas symbol off there, 2Na+ gas, plus the electron, plus the O- of the gas. And then the second electron affinity needs to go up because that's endothermic, because you're trying to attract an electron to something that's already negative, and so you need to overcome that repulsion. So our second electron affinity needs to go up.